In this video, let's see how an AR1 can be represented as an MLP. We'll be doing this specifically so we can feel the effect of the weight in the MLP. So let's look at the general models once again. We have for an MLP, we can have one input node and one output node. Notice there's no hidden layer here. Very simple architecture for the MLP. If that's the case, then we have a weight. I'll call it W1 because there's only one of them. And there's a theta of the bias term. Whereas we have an AR1 can be parameterized with a phi1. So we've just got xt minus phi1 hat. So this would be representing the estimate of phi1 hat from the data, or from phi1 from the data, times xt minus 1 equals the white noise term at, which is mean 0 and variance sigma squared a. So if that's the case, the W1 simply represents the phi1 hat. And note that there's no real role for theta here in the way I've parameterized the AR1, and thus the theta 1 here would be 0. So let's look at an example. So checking out WT Crude 2020, let's flip on over to our studio, and I've got it all dialed up here. There is our WT Crude 2020 data set, and note that we'll set the seed here to be 1, so we'll all get the same result. And all I've done here is fit an MLP, given it the data, said the frequency is 1, which is essentially effectively not going to have any periodic terms here in the model. We've got no hidden layers. We're going to tell it just to look at one input, which is xt minus 1, and there's no differencing, and we're going to give it reps equals 5. So it'll take the median of those 5 reps to give us the estimates. So I'm going to go ahead and run that. And we'll see that we'll make sure and double check the architecture is as we think it is. And there it is. That's xt minus 1. That's our output node. And we'll look at the summary of that we've seen in the book there. The MSE is 22.2019, 5 repetitions, median operator, so on and so forth. And we can access the weights by doing the AR1 MLP fit $net $weights. And if we do that, we'll get, these are our 5 repetitions that we did. And our 5th one here is 0.98543707 for the first weight. And that is our estimate of the bias term. Note that the estimate of the bias term is nearly 0. And this one is 0.98544. So let's flip back on over here and note that we have filled that in, the 0.9866, and that the theta here was represented almost by 0, but we'll come back for that one here in a second. So let's go ahead and see how, with Berg estimates, an AR1 would estimate it. So I'll go ahead and run that. And you can already see here that phi1 is 0.9866, but to phi1 hat, that is 0.9866. But if I isolate it with the $phi1, there it is, exactly 0.98655 rounded to 0.9866. And so if we flip up here, we see that that number is pretty close to this number, which the architecture of the MLP is trying to replicate the model, the AR1 type model. So kind of summarizing what we have over here, there's our AR1. And if we round, we get the same number up to 4 decimal places. And we have a theta here of negative 0.0039, which is effectively 0. So we can see and feel the effect here of the weight in this MLP model. Now, of course, in the MLP, we're going to have the opportunity to have a hidden layer with as many nodes or multiple hidden layers. And we can, of course, involve seasonality and differencing, and it's a very flexible model. So while it may not have the parsimoniousness of the AR1, and it may not have things like confidence intervals, all the bonuses that we get from a linear parametric model like the AR1, it may be more complex, but it may also have the potential. It doesn't always mean that it will have better predictive power, but it has the potential to have better predictive power, the MLP that is. So let's look at another example. This time, let's look at a generated realization. So we're kind of in a laboratory here. We know that phi1 is 0.72. So we'll flip on back over here and note that I have generated with Sn equals 1 the generated realization of 200 observations from phi 1 equals, we'll go ahead and make that 0.72. And we will go ahead and run that. And so note, there is the realization. And I'll go ahead and we got to turn this into a TS object. Note that the MLP needs a TS object to run. Can't just give it an array. So I'll go ahead and run that. And we'll let the, again, we'll set the seed of 1. We've done that. And we'll still give it no periodic behavior, no hidden layers. We'll just look at xt minus 1, no differencing, and reps of 5. Same idea. So we'll let it go ahead and fit that. We'll check it out. Actually, let's go up here just to be complete. Do a little sanity check. Make sure that we've got the same architecture. So we'll go ahead and run that. Yep, same architecture. We'll look at the AR1 fit. And finally, we'll look at the weights. And the weights here are about 0.672. And if we do the s.ar.w phi1, if we do that, we see that from given that particular realization, even though phi1 was 0.72, both of them are estimating about the same thing, right? It's 0.67, 0.67. And so if we flip on back over to our realization, we will see that W1 is indeed that 0.6722. And if we look over here at the AR1, we have that 0.6718, basically approximating the same quantity there. Our theta turned out to be estimated to be 0.0033, which is approximately 0. And this particular MLP architecture is representing a lot of what's happening in the AR1. So that weight, to feel the effect of that weight, is just weighting the effect of xt minus 1, just like the AR1 is. Now, let's do a little extra bonus here. Let's come on back over because we may not be satisfied with that, just to see that the MLP with gradient descent is working very similar to those Berg estimates in this particular architecture. So what I will do is, we can improvise here a little bit and say, hey, what if we took 1,000 observations? If we had 1,000 observations, shouldn't that give us a better estimate of the 0.72? So we'll still keep the SN equals 1, the seed of 1. We'll do that. There's our realization. Package it up into a TS object. And now let's see how well the MLP does. There's our architecture. And we will, much better this time, right? 0.72 rounded. And we can compare that with the Berg estimates and about 0.72, but both of them approximating about the same thing given the data. So that one would be, again, we know that phi1 is 0.72, and we can see it right here. Phi is 0.72, phi1 is 0.72, both of those estimating approximately the same quantity, and theta is still approximately pretty close to 0. So that's what we wanted to show here, is how to represent an AR1 as an MLP to get a feel for what the that weight is actually representing here as far as the relationship between xt and xt minus 1. So great job. Keep up the good work.